it's great to speak to you all this evening about Parker Solar Probe and the total solar eclipse. And I'll touch on more broadly why 2024 and 2025 are some of the most exciting years we've had for a while in heliophysics. So I have a few topics I'd like to get into. But just to start, I thought I'd tell you a bit about my journey to end up where I am. So I'm currently an astrophysicist, as Stacey said, at the Center for Astrophysics in Harvard Smithsonian in Cambridge, Massachusetts. But I've come quite a long distance to end up there. So I grew up in the United Kingdom, and I went to study physics at the University of Oxford back in 2012 to 2016. And I didn't really have any overlap with the sun as a science topic until in one of my summers, I had the opportunity to spend it in Dublin, and I spent it with the solar physics group out there. And I got to, for the first time, experience what it's like to do an astrophysics topic where you can really take very close-up pictures of the thing you're studying. There's not many things out in space that we can really see so close up, but with the sun, we can basically see all the detail that's happening all the time. And so that really captured my attention and made me want to study this further. And so from that summer to the next, I was lucky enough to get a second internship almost halfway across the world, in Berkeley, California, in the Space Sciences Lab, which is part of UC Berkeley. And so I got to extend my interest in solar from studying for close-up pictures of the sun to actually working on some instruments and learning some plasma physics. And I built on that to eventually wind up doing a PhD out there. And so I ended up staying not just for a summer, but for 6 years in California, which I graduated from in 2022 with my PhD. And while I was there, halfway through my PhD, in fact, the mission that I'll spend a lot of time talking about today, Parker Solar Probe, launched. And my advisor happened to be one of the people in charge of one of the instruments on board. And so I got to really be involved with the very first science of the mission. So that was a really exciting and great opportunity to be part of. And after graduating from Berkeley, I got to come out to where I'm speaking to you from today in the East Coast, so another 3,000-mile jump. And I stayed working with Parker Solar Probe, but changing from one instrument where we measured the electric and magnetic fields of the solar wind to studying its plasma content, which is the SWEEP instrument that Stacey mentioned in the intro. And so I've continued to work with Parker Solar Probe to this day, and I'm, I guess, about 7 or 8 years of working with this kind of science so far into my career. So that's a bit about me, but here's what I'll be talking to you about today, which is that 2024 and 2025 are a very exciting time to be in heliophysics. NASA is organizing a general engagement program called the Heliophysics Big Year, and if you Google that, you'll find loads of resources to get engaged. But I'm going to touch on 3 different topics which are related to this. So I'll come to at the end, the total solar eclipse that we're going to have in April, and the fact that we've had several in very close succession in the United States, which is a quite lucky coincidence that we've had. I'll talk about Parker Solar Probe in some detail and the science that we've been making since we launched in 2018. And to start with, I'm going to talk about solar maximum, which is something that basically motivates why we do this kind of science. In that it tells us how much the sun is having influence on where we are back home. So I'm going to start there and just explain what solar maximum is. So the sun goes through an 11-year activity cycle where at some points we're in solar minimum and there's almost no activity on the sun. And at solar maximum, there is lots of activity. And what do we mean by activity? There's lots of different things. Basically, anything you measure about the sun is more active during solar maximum. In this plot, you can see what the sun's disk looks like over the course of a solar cycle. And you can see during, for example, 2014, 2015, there's loads of splotchy hot plasma all over the disk. Whereas if you go all the way to 2020, in the top right, there's almost nothing on is kind of featureless. And another way to measure that is how many sunspots we can see on the disk. And that's a measurement that people have been making since the 1800s, because that's quite an easy thing to see. And this plot on the right then shows that where we are today is the black and purple data. And that is reaching what we think will be the peak. We have models, which is what the red smooth line is. And you can see that that's a difficult thing to predict. And that's one of the reasons why this is a very active area of research. Is we don't exactly know how to predict when the maximum is going to happen, but we're pretty sure it's going to happen soon. Whereas if you go back to 2020, which is not that long ago and was more like that. The sun was more like this when the Parker Solar Probe launched. It was that was the solar minimum. So this is just showing you that the sun changes over 11 years, but how does that factor into what we care about on Earth? So just to show you again, on the left, this is what the sun looks like when it's dead quiet, like it was back in 2020. And on the right, this is a picture of the sun from this weekend. So again, it's very active right now, and we're expecting this to be getting to the peak very soon. But yeah, so why should we care about this? So looking at the static images of the sun, you can see there's lots more stuff on it, but it's not very clear that that should mean anything for us back on Earth. But if we, instead of looking at static pictures of the sun, we look at what it's doing dynamically with a movie, you'll see that at solar maximum, they throw off lots of material. And what you're seeing in this movie is there's a black circle here where we plotted out the surface of the sun, much like what happens during an eclipse. And you see these shapes moving off in all directions. And these are called coronal mass ejections, which are big ejections of plasma where the sun's throwing off large amounts of its atmosphere and they're flying through space. And sometimes you'll see these things come at you. And instead of looking like a shape that's moving to the side, it looks like a circle that grows. And when you see one of those, you'll see that the camera here has all this speckling around it. And what's happening is that coronal mass ejection is coming straight at Earth, and it's accelerating particles, and those particles are actually getting to this camera, which is situated in space between us and the sun, and causing the camera sensors to like light up with noise. So basically, when the sun is active at solar maximum, it's sending lots of energetic stuff our way, and that can affect us back on Earth. So one way that we see this effect on Earth is with the aurora, which is of course a super beautiful and not terribly threatening idea, but it's something that we see lots more of during solar maximum. And what's happening is that those ejections that we were looking at are essentially gaining access into the lower atmosphere, and those same energetic particles that were causing the cameras in space to kind of fuzz up a bit, they get down into the lower layers of the Earth's atmosphere, and they interact with our atmosphere, and they cause this basically electric and magnetic fields and glowing, and you're basically seeing the imprint of the sun's ejections in the night sky at the poles of the Earth. So that's a really beautiful and spectacular phenomenon, which I personally have not seen in my life yet, and I would love to one day. But there's lots of other ways in which the sun can affect us. And here's just a few examples. And this is really a motivation for why we study this field, because any of these things are quite important for our current day-to-day lives. And so the better we can do of predicting how the sun is going to affect us, the better a job we can do of safeguarding us from some potential issues. So for example, if you're out in space as an astronaut or a satellite, you really don't want to be hit by huge amounts of radiation unexpectedly. You want to know that things are coming your way and to be able to make preparations to be safe. The aurora we already touched on, but other stuff back on Earth starts to respond to solar eruptions. So for example, radio signals have a harder time propagating through around the Earth during solar storms. So things like GPS signals and radio communications can suffer from disruptions. Similarly, airlines rely on this kind of infrastructure, and so they want to know when the solar storm is coming their way. And one other effect the sun can have is on our power grid. So it can actually generate currents in our power lines and potentially short out transformers or other electrical infrastructure. And we have ways to prepare for this if we know it's coming, but the better we can do with getting advance notice, the better we can mitigate any problems. And there's actually a whole organization in the US called the Space Weather Prediction Center, whose job is to do the state of the art in predicting space weather, is what we call it. So that's broadly why we do this kind of science, because the sun ultimately affects us back on Earth. But to understand it at all, we need to really study all of the way back at the sun, how it works and how it generates the energetic stuff that we've just been talking about. So we'll move on to talk about Parker Solar Probe. which is a mission that NASA has sent to be the closest we've ever got to the sun in our history of the space age. And as I said, I've had a large involvement with this mission in my career so far. And I'd love to tell you a bit about the mission and what we've seen so far. So like I said, the mission launched during the middle of my PhD, and I was super lucky to be able to travel out to Cape Canaveral in Florida to see the launch. And this picture you can see here was taken with my phone camera, and that glowing yellow dot is the spacecraft about a minute after launch, just a little after the rumbling of the sound waves gets to you where you're watching from. And if you could zoom way into that, you would see a gigantic rocket, which you can see at the bottom right of this slide, which is called a Delta IV Heavy. And in the very top nose cone of that is the spacecraft Parker Solar Probe, which was at that time tucked up and safe before it was released out in space. But this is basically one of the largest rockets available at the time to get us the boost into space. But the reason that we need such a big rocket might actually be a little counterintuitive, because it's not because we need to make the spacecraft go particularly fast. It's actually because we need to slow down relative to the Earth. So the Earth is going around the sun very quickly, and to get close to the sun, we basically need to lose the Earth's momentum that it has around the sun. And so this rocket essentially provides a lot of thrust in the opposite direction to which the Earth is moving, and that causes our orbit to fall in towards the sun, and we could really get close in. And here's a professional time-lapse photography of the launch, where you can see the rocket taking off over time and streaming off to the horizon to go on towards the sun. So once it gets out into space, this movie shows its trajectory. So you can see it leaving the Earth there and falling into this ellipse. And you see it gets somewhat close to the sun, but it still has some way to go. And of course, once we've left the rocket behind, we don't have any way to burn our thrusters to bring it closer. But what we do still have the power to do is to use the planets to change the orbit. So you'll see every so often in this movie, you will come very close to Venus, and that twists the orbit just a little more and gets our perihelion, the closest approach to the sun, to get closer and closer over time. And so even from the very first orbit, we were the closest object ever, the closest object made by humankind to go into this orbit close to the sun. But the orbit is just tightening and tightening over time. And one thing I'll come back to at the very end of this talk is that we are basically going to break our own record in December of this year, and we're going to reach the very closest approach of the mission. So what's on board the spacecraft and how does it work? So obviously a big issue with getting close to the sun is the fact that you have a large amount of solar radiation trying to heat you up. The sun is very hot, as we know, and we want to survive and measure stuff in its hot atmosphere. So one of the most prominent features on the spacecraft is the heat shield, which is this large kind of octagonal shaped plate on the front. And the very front of that is very, very bright white, and it reflects a lot of the radiation of the sun. And then right behind it, these kind of large conical shape on the front is a bunch of radiators, which use water to basically radiate the heat that the heat shield is not managing to get rid of to space. And then finally, back towards the spacecraft is the actual like computerized system itself, which is kept safe from the heat. So while the front of that spacecraft gets to around thousands of degrees, the back of it is only 70 or so. So nice and cool. And that hosts a load of different components. A couple you can see are the solar panels. There's an antenna for talking back to home, and there's several science instruments. And most of them you'll see are shielded behind the heat shield, but there are a couple of exceptions. So in particular, the antennas stick out around the side, and this instrument that was built in my institution, the Center for Astrophysics, is called the Solar Probe Cup, and both of these things basically stick out around the side of the spacecraft and see the full brunt of the sun. You can see it being built in the clean room on the right there, the Solar Probe Cup. So these things had to be designed with very exotic materials to withstand the heat of what they were going to be experiencing in space. And 6 years on, these are all working great. So it was a great engineering endeavor. So a couple numbers that you might be interested in. So the closest approach that we'll get to the sun is 4 solar diameters away. We'll see that later in the context of the eclipse, which is 4 million miles. It sounds like a large amount, but when you compare it to the Earth, which you can do on the, if you look at the cartoon on the right, you see if you were looking down at the sun from the Earth, the spacecraft is basically 10 times or greater closer to the sun than where the Earth is. So by astronomical standards, we're super, super close. And as you get to perihelion, you don't just get close, you speed up. And the speed we reach the closest approach is 430,000 miles per hour, which if you were back on Earth and traveling from LA to Boston, it would only take you 21 seconds to make that journey at that speed. And then one of the number I mentioned just before is that the heat shield gets up to thousands of degrees, and it's keeping the back of the spacecraft nice and cool at the same time. So why are we getting so close? So I said that we were ultimately trying to understand the sun's extended atmosphere, but what don't we know about it? There are some key questions that the mission is trying to probe. One of them is called the coronal heating problem. So when you look at the sun in the sky, you're seeing its visible disk, what's called the photosphere. And that is at a nice and cool 5 or 6,000 Kelvin, so thousands of degrees. But if you go a little bit out from the surface into what's called the corona, you see the temperature climb, and it climbs not just by a little bit, but by a factor of 1,000. You get to millions of degrees. And the physics of how that heat is transferred to the corona is something we don't really understand, and it's pretty fundamental to understanding how the sun generates its extended atmosphere and creates a solar wind. Another key question that the mission is trying to address is that when you get far from the sun, the plasma you see everywhere is traveling away from the sun. So the sun is expelling its atmosphere in all directions. And that creates the flow that we call the solar wind, and the Earth and all the planets sit inside this solar wind with this plasma running outside of us. We're protected by the Earth's magnetic field, but that's basically the medium that we live in. And to get from basically not moving back at the sun's surface up to supersonic speeds, that's a physical process that we're still trying to understand a bit better. And then one of the other key questions of the mission is to do with those energetic particles we saw interfering with the camera earlier. We basically know that these particles are created and they have very, very high energies, and they are potentially hazardous, but we still have lots of questions about how they actually got those energies in the first place. So that's the key questions the mission is trying to address. And now here are some findings from the mission so far. So you might have heard us mention that the mission is destined to touch the sun. So the mission isn't actually ever going to land on the sun or touch its photospheric surface, but we did pass a very key milestone just a couple of years ago, where we crossed a surface that's called the Alphane surface. And this is very important to the first problem I just showed about understanding how the sun's corona is so hot, because basically this is a surface around the sun that is a boundary between where the sun's atmosphere is sonic to supersonic. And inside, where it's subsonic, you can have waves traveling back and forth between the sun's surface and interacting with each other. And that has different heating properties, different ways that physics can explain heating to be transferred to the surrounding medium, whereas outside, the waves don't have the same property. And this is basically a fundamental parameter to a lot of our models of the sun's atmosphere. And so we verified that we were for the first time crossing that boundary. Now that's back in 2021, we crossed it for the first time. And essentially, as we go back and forth multiple times over many years, we're going to build up our understanding of the physics of how the sun's corona is heated. Another thing that the probe saw from its very first orbit through to now is that the solar wind is full of little spikes in the magnetic field. It wiggles in the magnetic field, which look like jagged shapes. They are essentially, well, the scientific community has taken to calling them switchbacks, in that the magnetic field is bending back on itself and pointing back from the direction it came. And the solar wind is essentially filled with these things. And this is really exciting because it's something that wasn't predicted but it is clearly an important feature of physics that we need to explain to understand the solar wind. These things carry energy, and they possibly tell us about stuff going on back at the sun that's creating its atmosphere to its expanding atmosphere. One of the instruments on the mission is a camera called WISPR, spelled WISPR. And this camera couldn't look directly. But what it does do is look forward in the direction the spacecraft is traveling. So the spacecraft travels sideways around the sun. And basically the WISPR camera looks at the direction of the sun that the spacecraft is moving. And when you get close to the sun, that means that you're threading between different structures that are coming out from the sun. So when we look at the eclipse later, we're going to see these things called streamers, where there are large blobs of dense plasma coming outwards radially from the sun. And if you look in this movie, what you'll see is that there are sometimes these features which point diagonally upwards or downwards, and they're sweeping out at the top of the frame and the bottom of the frame. So they're going over us. We're flying between them. So we're not just seeing this stuff from afar, we're really flying through it. The other thing you can see in this movie is the galaxy, the Milky Way. It comes out very nicely when you have a very dark night sky, as you do in space, unlike in Earth. And another thing WISPR has seen recently, so earlier we were looking at these coronal mass ejections coming from the sun, so large ejections of plasma. And again, most commonly from Earth, we can see these things traveling outwards and away from the sun. But now with Parker, we are actually able to fly through these things. So you're looking at a similar movie right now where there's not much going on, but you'll start to see there's some stuff flowing out, and eventually you see this huge structure fill the field of view, explodes past us, and it's moving sideways, like beyond where we are. So we're flying into this thing, and we basically fly behind it and see what it left behind. And so that's something that could never be done unless you were actually flying really close to the sun. And then one last science topic, we use Venus, as a reminder, we use Venus to change the orbit of the spacecraft to get closer to the sun over time. But one thing that wasn't guaranteed at the start of the mission, but it turned out that it was feasible to do, was that we could turn on the instruments when we were close to Venus. So we could do science around Venus that we didn't know we could do when we planned the mission, but it turned out to be very fruitful. So there are two examples of many, but two examples here. One is the camera on the spacecraft was able to look at Venus's surface. That's the image on the left here in gray, and it could see surface structure, which you could infer was there if you used radar. But this is looking in light that we could mostly see with our own eyes and some infrared, some heating. And what you're looking at is a large elevated region of the planet. And the reason you can see it is because Venus is covered in clouds mostly, so it seems kind of strange that you'd be able to see anything at all. But Venus's surface is so hot that it basically glows. And so you're looking at this hot, glowing surface of the planet kind of coming through the clouds. And we were able to pick that up with Parker Solar Probe's WISPR camera. Another thing that the spacecraft has been able to investigate is whether there's any lightning happening on Venus. Because we have these antenna and magnetic field sensors, which we use for studying solar wind, but they can also be used to look for the signatures of lightning. So it's quite an open question about whether lightning can happen on Venus. We know that it happens on Earth, but we don't know about Venus. And so far, Parker Solar Probe has not seen any measurable detection of lightning happening on Venus when it's been close to it. So that was what I had to say about Parker Solar Probe. And then I just wanted to turn to the total solar eclipses that we're having in the US this year to wrap up. So I'm sure everyone knows this, but to remind you what an eclipse is, it's when the moon aligns between the Earth's day side and the sun, and the moon just happens to be the right angular size in the sky. So it's much smaller than the sun, but it's much closer. And it just happens to be the right angular size that its disk basically is the same size in the sky as the sun. And that leads to the situation where it can block out the entirety of the sun and cast a shadow on the Earth. Here's an example seen from space, where you can see the large shadow cast by the moon landing on the planet. And so if you're standing in here, you see basically the sun go dark. So there are a few different kinds of eclipses. The most exciting are total solar eclipses, which is when the moon's disk entirely blocks out the sun, the visible surface of the sun, that is, the thing that's at 5,000 Kelvin. And when that happens, much like how I said we block out the sun to do scientific observations of the corona, the scientific kind of implication of a total solar eclipse is that you block out this really bright stuff, and what you're left with is the sun's corona, this thing that's billions of degrees and of great interest to science. And you just barely block out the edge of the sun, so you really get to see what's going on with the sun's corona right down low, close to the sun. You can also get an annular eclipse, which happens because the moon isn't always the exact same distance from the Earth. It changes during its orbit. And it can happen that the moon is a bit further away from the Earth during an eclipse, and it can be far enough away that it doesn't quite cover the whole sun. So in that case, you get an annular or ring of fire eclipse, which is something that happened in the US back in October last year. So these things are also quite spectacular, but because you have a tiny bit of the sun's surface peeking out, you don't get the same effect. It doesn't get properly dark. It doesn't get dim enough that you can see the corona, but it's still extremely spectacular. It's also not safe to look at with the naked eye. And then the third type of eclipse is a partial eclipse. And in fact, this is what you see during a total solar eclipse before and after. And also, as I'll show in a slide or two, most of the US this April is going to see a partial eclipse, even if only a small part will see a total. And so in this case, you're not exactly aligned with where the moon is going between the sun, and you only see a bite taken out of the sun. And again, that doesn't short out the brightness and leave the corona visible. But again, it's super spectacular to see. So the US has been kind of uniquely lucky in terms of eclipses in the last few years. So there was a total solar eclipse in 2017, which started in Oregon and went down to South Carolina. And if anyone remembers this eclipse and was there for it, feel free to put in the chat where you were and what you remember seeing. So this was a total solar eclipse. I was able to be in Oregon for it. It was actually just before I started studying coronal physics properly, so I didn't quite have the scientific interest that I have today. But that was just 7 years ago, we had this total solar eclipse. And then last year in October, we had an annular eclipse, which again went through Oregon, I believe, and ended up in Texas. And these blue arrows show how the eclipse moves in time. It travels across the country from left to right, to do with where the moon is in its orbit at the time. So that annual eclipse happened in October, so only 6 years after the last major eclipse, we had another one. And now in April 8th this year, so next month, we're going to have another total solar eclipse, and this one is going to start in Mexico and enter the US through Texas and exit through the Northeast into Canada. So 2 in 7 years is a really fortuitous, and in fact, the next eclipse after this one won't be until 2044 or 45, I think. So it's really worth looking out to see if you can see this one. And of course, because it hasn't happened yet, we don't know what this one looked like, and everyone in coronal and heliophysics will be excited to see what we can see in the solar maximum corona. So there'll be a huge number of scientific experiments as well as public events to look at this eclipse. So this is a bit of a broader picture of the geometry of this eclipse. And again, you see that the path of totality is a narrow band, and it goes through Texas and it goes to Northeast. But the whole of the US, no matter where you are, is going to see some part of an eclipse. So even all the way to the southeast in Florida, you'll have 50% coverage at the peak. And up in Washington, there'll be a 20% bite taken out of the sun. And the closer and closer you are to this path of the total solar eclipse, the more extreme coverage you'll see. And then if you are lucky enough to be able to be in the path of the total eclipse, then you'll see this entire occultation and the corona appear in the night sky. So as a reminder, it's not safe to look directly at the sun with your naked eye, except for the few minutes when the totality occurs. So for any people looking in outside of the path of totality, you should be wearing eclipse glasses or using another way to project the sun. So that's true no matter where you are. If you're outside of the path of totality, and even if you are in the path of totality, it's not safe to look at until the total coverage happens, which again is only for 4 or 5 minutes. If you look on the image on the bottom left, that's kind of the progression you'd see during an eclipse, and it's just a few minutes in the middle where all of the bright part of the sun is hidden. But once that happens, it really is a unique and spectacular thing to see. The entire world changes. The sun sets in a horizon that goes 360 degrees around you, not just in the east or the west. And you hear all kinds of stuff go on in nature as well as the celestial phenomena. And just to wrap up, the final thing I want to do is bring Parker Solar Probe back into the picture. So this is showing what you can see with a really high resolution camera during an eclipse, and you give it a long exposure and you see the bright features pop out. And you're looking at what I was calling streamers earlier, these large extended fingers of plasma coming off from the sun, and you can see them going off to the edge of the image here. And I was saying earlier how Parker Solar Probe flies between these things as it's going close to the sun. It's basically seeing these things pass overhead and below it. And I just wanted to put that in perspective that during its closest approach, Parker Solar Probe is really just a few solar disks away. So it gets to well within the field of view of this image. And in fact, in this eclipse coming up, while you're looking at it in the sky, Parker Solar Probe will just be off to the right, taking its science data. And these, so it's really deep inside the corona, and is measuring scientific data about what you can see during an eclipse. And that's where it is currently. And this December 24th this year, it will actually make its final adjustment to its orbit, shrink itself down another half a solar diameter. And that will take us to the final achieved closest approach of the mission, which it will stay in for hopefully many years to come. And so that was what I brought to talk with you today about. So I hope you enjoyed my presentation, and I'd love to take any questions. So thank you.